TBL is going to be a little bit difficult with this
arrangement. Yeah, this year is exceptional. They said, I heard them say that this year is exceptional.
Hopefully the other daughter
Free
will be featured. So.
شغلك الكرسي.
Okay, everyone? Okay. Are we all seated? Okay, so we can finish early. Okay. Okay, so good morning, everyone. So today's lecture is one of my favorites. It's on the laws that govern the movement of ions. So we, in the previous lectures, we talked about, different mechanisms through which, molecules are transported to the inside or outside of the cell, right? And so we said that certain molecules are, can, very easily pass the membrane, and some requires the help of proteins in order to get in or out. And some of those, transports are active. They do consume energy by going, against their concentration gradients, while others are passive, right? And so in today's lecture, we will learn about the charged ions, how, what are the laws that govern their transport to inside or, to outside of the cell, okay? And so, as we've already learned that the concentrations of ions or different molecules are different in the intracellular environment compared to the extracellular environment. And this is very important in order for the cell to be compatible with life. It has to maintain We said that there are, different concentrations of ions and molecules in the intracellular environment compared to the extracellular environment. And this is very important in order for the cell to perform its function. So the certain concentrations of ions has to be within a certain range in order to be compatible with life. The most important ions that we will come across is the sodium. As you know, that sodium is highly concentrated outside compared to inside. Potassium is the opposite. It's highly concentrated inside the cell compared to outside. Chloride is same as sodium, where there is plenty of chloride in the outside compared to the inside of the cell. And so these concentrations are created, or they are unevenly distributed because we have a semi-permeable membrane. Remember that the membrane, the phospholipid layer, restricts certain molecules from entering or exiting the cell, right? And there are channels which are gated. They would only allow certain ions to get in or to go out if there is a certain stimulus. And so because of this, we have this uneven distribution of ions because of the property of the semi-permeable membrane that the cell has, right? And also we have active bumps. So this is the first factor, is that the semi-permeable membrane. We also have bumps, which we said they do consume energy, right? In order to move ions against their concentration gradient. So we have the sodium-potassium bump, which what it does, it moves 3 sodium against, their concentration gradients to the outside where there is plenty of sodium, okay? And concentrate potassium, so it moves 2 potassium from outside to inside to concentrate, to keep the levels of potassium inside the cell high, okay? So these 2 factors create this uneven distribution of the ions inside and outside the cell. And so because of this, now we have a higher concentration of potassium inside the cell, right? And so when we have a channel, okay, a potassium channel that has been, opened, this means that potassium will run down its concentration gradient, right? So it will run down its concentration gradient from inside to outside. Now, potassium has a charge, right? It has a positive charge. It is an ion, a charged ion. It's a cation, okay? So it's positively charged. And so as it moves to the outside, as you can see here, the inside will gain, negative charge because the inside is losing more of the cations, the positively charged ions, which is in this case, potassium, okay? And so this change is called a diffusion potential, which is the potential difference generated across a membrane when a charged ion diffuses down its concentration gradient. So this is called a diffusion potential. Similarly with sodium, so sodium we said is higher outside the cell compared to inside, right? And so when we have a sodium channel, which now is opened in response to a certain stimulus, as we will learn in the upcoming lectures. So when this sodium channel is open, sodium will move down its concentration gradient from outside to inside. Now, sodium is a cation, it has a charge, it's positively charged. And so as it moves to the inside of the cell, the inside of the cell will gain more positive charge, okay? And so this movement of sodium, okay, is what creates this diffusion potential, okay? And so a diffusion potential can be generated only if the membrane is permeable to the ion, okay? So there wouldn't be a diffusion potential if there is no permeability to the ion. We will see this in a second. And what governs, or what, the laws that govern the movement of these ions are 2 forces. The forces that govern the movement of these ions are 2, the concentration gradient, okay, as well as there is an electrical force, okay? So let's learn about these forces, okay? So the first force is the chemical driving force. This is very easy, as you know, that molecules, solutes, or ions, they will move from areas of high concentrations to area of low concentrations, right? So if we have, a highly, we have an ion or a solute that's higher, has higher concentrations inside than outside, then there is a chemical driving force for this ion to go to the outside, okay? Similarly, if it's higher, it has higher concentrations in the outside than the inside, then there is a chemical driving force for that ion to go to the inside. Is this clear? All clear? Okay. And so that's number 1 is the chemical driving force. The number 2 is the electrical driving force, because remember now we are talking about ions, which, they have charge, okay? And so we know, like from experiments, that inside the cell, has more of the negatively charged solutes. It has more, negative charged proteins, etc., which make the inside of the cell more negative in the resting state compared to outside, okay? And so because we have more of the negatively charged in the inside and more of the positively charged in the outside, and we have here the plasma membrane, right? And so the plasma membrane is semi-permeable, okay? And it only allows certain molecules to pass from the inside to the outside or vice versa. And so because of this separation of charge, okay, so now we are separating these two environments which have different charges. Because of this separation, there is, a voltage, okay? We are creating a voltage. It's like the battery, okay? We all know the battery, right? You guys know the battery, we use it in everyday life. And so the battery, the way it works is by separating the negatively charged molecules in one end, okay? So this end is the negative end and this is the positive end. And you know that the negatively, charged ions or molecules, they love to go or attracted to go to the positively charged ions, right? They are attracted to go to the positive side. And so because here we are separating the negative, charges from the positive end, okay, once we connect, we put a wire here that is connected to the, to the cathode where the, where it's positive, these electrons will rush to go to the positive side, okay? And so this is how a voltage is created by separating the charges, okay? And so, when scientists measure the resting membrane potential or the voltage inside the cell, so here we have a neuron. Let me see. So here we have a neuron, and so what they did, they inserted an electrode, okay, which basically measure the voltage inside the cell. And so it appears to be around negative 86 millivolts. So the voltage is measured as in voltages, okay? So the bottom line here is that there is a chemical driving force for the movement of ions, and there is also an electrical force that, pushes the ions to move. So we will learn more, we will understand this in a clearer way in a second. But the bottom line is that positively charged ions are attracted to go to the inside because the inside has more negative charges, right? And the opposite, the negatively charged ions in the inside are attracted to go to the outside because the outside is more, enriched of the positively charged ions. Is this all clear? Clear? Okay, so let's take this as an example. Okay, before we go in there, so what governs the movement of ions is the sum of those two forces, both the chemical as well as the electrical driving force. So as you can see here, we have potassium, okay, and potassium is a positively charged ions, okay, but we have a high concentration of potassium in the inside than outside. So there is a huge chemical driving force for potassium to go from the inside to the outside. But also we know that potassium is positively charged, okay? And so there is also an electrical driving force for potassium to be attracted to go to the inside where there is, high of the negatively charged ions. And so the sum of those two, driving forces, the chemical and the electrical driving force, will determine to which direction the potassium will move, okay? So let's take an example in order to understand this more clearly. So let's take this example. So let's say here this is inside the cell, okay? and this side is outside the cell. And here we have the, the membrane, which in this case, we have no channels in there, and there is no way that potassium will move, okay? Because there are no open channels, okay? Is this all clear? Now, we have higher concentrations of potassium in the inside and lower concentrations of potassium in the outside. And so in this case, in this scenario in A, there is no net movement of ions. There will be no movement of potassium. Why is that? Because what? There are no channels, right? Although there is, higher tendency for potassium to move if there was a channel open. But in this case, we have no channels opened. And so there will be no net movement of ions. Now, if we insert a potassium channel that is only, permeable to, that would only allow potassium to move. So here we are just inserting potassium channels that exclusively would allow only potassium to move. And so in this case, because we have a high concentrations of potassium inside the cell than outside, there is a huge chemical driving force, okay, for potassium to move from inside the cell to outside. And so as potassium moves, so start moving, as potassium moves, as you can see here, the inside of the cell start gaining, becoming more negative because the inside is losing more of the positively charged ions. And outside the cell is gaining more positive, positivity because of the, potassium is going to the outside. And so as the positively charged ions are building up outside the cell, and the negatively charges are building up inside, at some point, potassium will be attracted to go to the inside. And so at certain point, there will be, the movement of potassium would stop because the chemical driving force and the electrical driving force are opposing each other. And in that state where there is, this, counterbalancing of the two forces, and where potassium ions movement would be stopping, this is called the equilibrium. This is said to that potassium has reached its equilibrium state, okay, where no longer potassium would be moving because the chemical driving forces are counterbalancing the electrical driving forces. Is this all clear? Clear? Okay. So there is actually a formula where you can calculate the equilibrium potentials for the individual ions. And so this formula is called the Nurnist Equation. Okay, where it takes into consideration, multiple factors, the most important of which is the charge of ion. It's very important to be taken into consideration, that formula, as well as the concentrations of the ions outside and inside. And so if we calculate all of this, okay, it's very easy. If we calculate all of these are mostly constant. It will come down to 61, okay? So the formula will become like this, the 61 over the charge of the ion, whether it's positive or negative, log the concentration of the ion outside over inside. So let's take this example where, let's say, inside the, the cell, we have 10 millimolar of potassium. Okay, and outside we have a 1 millimolar of potassium. And so if we calculate this, we know that potassium is a positively charged ion. So it's going to be positive, right? So positive 61 log 1, which is the concentration outside over the concentrations inside. And so the equilibrium potential for potassium, so this is EK, this is the equilibrium potential for potassium, would be negative 61 millivolt. So this is this number represent the voltages at which the movement of potassium would be stopping. There would be no net movement of potassium. This is the equilibrium potential for potassium. So if the concentrations of potassium in the outside was 100 milli, in the inside was 100 millimolar, then the equilibrium potential for potassium would be negative 122 millivolts. If it was 1, then it would be 0 millivolt, because you know there is 1 millimolar inside and would be 1 millimolar outside. Okay, is this all clear? So let's take this as an exercise. Anyone can calculate for me the sodium equilibrium potential given these concentrations? Anyone? Yep. Yep. 10? Try again. Simple math. Yep. 61. Very good. Is it negative or positive? 61. Positive 61. What did you get? Huh? 61? What? I don't hear, I cannot hear you. Negative 61? Try again, because here is the outside is higher than the inside. You did that? What did you get? So it's not, you know, 1 over 10, it's 10 over 1. Okay? Yep. I cannot hear you. So if you calculate, so the formula always is you have to put the concentrations of the outside over the concentrations in the inside. And also you have to put in the charge of the ion. So in this case, sodium is positive charge, right? So when you calculate, but if it's chloride, then when you calculate, you would do negative 61. Okay, log the concentrations outside over inside, okay? Whereas if it's sodium or potassium, you would do positive 61, log the concentrations outside over inside, yep? 61 is constant, okay? So it is positive 61, okay? So what does this mean? Okay, what does, you know, positive 61 mean or negative 61 means? Basically what it means, if we, let's take, because what we mentioned is a theoretical scenario. Let's take, you know, a real example. So here we know that the concentration, these are the concentrations of sodium and potassium, okay? And so if we calculate the equilibrium potential for potassium given these concentrations, what we will get is that the equilibrium potential for potassium is negative 94 millivolt. Sorry, I didn't put that. So millivolt. So the equilibrium potential in real scenarios would be negative 94 millivolt for potassium. And for sodium, it would be positive 61. So what does this mean? It means that if the membrane was only, okay, only with 2 lines, permeable to potassium, then the membrane potential for the cell would be equal to the equilibrium potential for potassium, okay? And if it was that the membrane was only permeable to sodium, then this means that the potential, the membrane potential of the cell would be equal to positive 61 millivolts, okay? But we know from experiments that the resting membrane potential, okay, of the neuron in this case is around negative 86 millivolt. Why is that? Why it's not really exactly equal to the equilibrium potential for potassium, and it's way, way, way far away from the equilibrium potential of sodium? Why is that? Anyone has a hypothesis? Yep. I cannot hear you, Wallah. Yeah, but why it's closer to potassium? So here it's negative 86, right? And the equilibrium potential for potassium is negative 94, right? So why it's closer to the potassium, but not far, far away from the sodium? Yep, yeah. Exactly, excellent. Because the membrane at rest, we will learn this in the next lecture, at rest has a higher permeability to potassium than to sodium. Still, sodium, has some permeability because we have non-gated sodium channels, but very low compared to potassium. And this is why the membrane potential is much closer to the equilibrium potential for potassium, but not to the sodium. So let's take this. So we said here is the membrane potential for the cell. So this is the VM. The membrane potential is, let's say, negative 74. Okay. This is in normal conditions. And so we know that the equilibrium potential for potassium is negative 94 millivolts, while sodium is positive 61 millivolts. Now, why the membrane is closer to the equilibrium potential for potassium? Because there is higher permeability at rest to potassium than to sodium. However, if we insert a channel, a sodium channel that now is open, there is a huge driving force for sodium to move from which side to side? Yeah. Outside to inside or inside to outside? Outside to inside, right? Because we have a huge amount of sodium outside, right? And so if we insert a channel now that is open for sodium, there is a huge driving force for sodium to go to the inside of the cell. And this can be calculated, the driving force, by subtracting the membrane potential from the equilibrium potential for the ion of interest. Okay, so let's take, for example, sodium as an example. So it's going to be negative 74, which is the membrane potential at rest, right? And negative 61, right? So this would be equal to negative 135 millivolt. So there is a huge driving force for sodium to go to the inside of the cell, okay? And so the ions, so this is very important, ions would move in the direction that it will take the membrane to its equilibrium potential. Now, what does this mean? Now the membrane is negative 74, right? And sodium, the equilibrium potential for sodium is positive 61. So it is in the interest of sodium to go to the inside, because sodium is a positively charged ion, right? And so it's in the interest of sodium to go to the inside in a larger amount in order to bring the membrane potential to its equilibrium potential. Okay, you see that? Because sodium is positively charged. So this is the cell. Now inside the cell, we have the membrane at -74 millivolts. And outside, the sodium equilibrium potential is 61 millivolts, positive 61 millivolt. This is the equilibrium potential for sodium. So it is in the interest of sodium, because it's a positively charged. So once sodium go to the inside of the cell, it will make the inside of the cell more positive or negative? Is it more positive or negative when sodium goes to the inside? It will become more positive, right? And so now when sodium goes to the inside of the cell, it will make the inside gain more positivity. And so it is in the interest of sodium when it moves to bring the membrane closer to its equilibrium potential. So it wants the membrane to, go a little bit, towards the positive values from -74 to reaching positive 61 millivolt. Is this clear? While for potassium, for example, let's say, for example, that the membrane is at -10 millivolt, okay? So let's say now the membrane is at -10 millivolt. Now, if we open the potassium channels, okay, there will be a huge driving force for potassium to go from the inside to the outside. Why is that? Why is that? Anyone? Yep. Very good, because potassium, the equilibrium potential for potassium is -94 millivolt. So it is in the interest of potassium to exit the cell, because when the potassium exits the cells, it means that the inside of the cell is gaining more negativity. And so in this way, it will take the membrane towards its equilibrium potential. Is this all clear? Is this all clear? Yep. We are talking here about the equilibrium potential. So the equilibrium potential for sodium is +61 when we calculated with the Nurnist equation, right? And the membrane, we know that the membrane is at -74 millivolt, right? And so it is in the interest, when we open the sodium channels, it is in the interest of the sodium to make the membrane goes towards its equilibrium potential. So it will be moving to the inside to make the inside more positive, to bring the membrane to here, to the positive 61 millivolt, okay? Whereas if the membrane was here, if the membrane was, at this, let's say, positive 50 millivolt, okay? And when we open the potassium channels, let's take this as an example. It is in the interest for potassium to go from the inside to the outside, because it wants the inside of the cell loses positive charge to make it makes it more negative, to brings it to its equilibrium potential, which is -94 millivolt. Okay, is this clear? Okay, good. And so in order, this is what I explained. So we are taking into consideration both the chemical driving force as well as the electrical driving force, which is the electrochemical driving force. And so this can be calculated by the formula, which I just mentioned, which is Vm minus the equilibrium potential for that ion. And so one way, okay, so in addition to what I explained, okay, like a shortcut to know to which side the ion is moving is by looking at the sign of the result when you calculate the driving force. So let's take this as an example. So here we have the equilibrium potential for potassium, which is -94 negative 94 millivolt, right? And the membrane potential is negative 70 millivolt. So when we calculate the driving force using this formula, what do we get? We get plus 24 because negative 70 minus become, so minus become positive, right? 94. And so in this case, it will become positive 24, okay? And so some people, this is a trick to know to which direction the ion is moving. If you see that the sign is positive, it means that the movement of this ion is outward, okay? So potassium is going to move from the inside to the outside. So it's an outward movement. Whereas for example, in this case, if the equilibrium potential for potassium is negative 94 millivolts and the membrane potential is negative 100 millivolts, the result when we calculate Vm minus the equilibrium potential for the ion would be negative 6, okay? And so when you see the negative sign, it means that the movement is inward. So potassium will be moving from the outside to the inside. Why is that? Regardless of the sign. Why is in this example, in the second example, potassium should be moving from the outside to the inside? Why is that? Why is that? Yep. Exactly. Notice that the membrane potential is negative 100 millivolts, right? It is negative 100. And the equilibrium is less for potassium. It's negative 94. And so when potassium go to the inside, it will make it less negative because it wants the membrane to reach the equilibrium potential for itself, for the potassium. Okay? Is this all clear? Clear? Any questions? Yep. Exactly. So ions will move in the direction that it will take the membrane towards its equilibrium potential. Okay? Is this all clear? Yep. So it depends because, sorry, your question again? It depends. It depends on the concentrations, whether the chemical driving force is higher, than, or the electrical driving force is higher. So it always depends on the sum of the two forces. Okay, if there was a huge, concentrations of potassium, for example, in the inside than outside, there is a huge chemical driving force for potassium to leave the cell. Okay, and so the state where it's, both forces are counterbalancing each other, this is the equilibrium potential, and which can be calculated by the Nurnist equation. Okay, this is all clear? Okay, good. And so the membrane potential, okay, so we will learn more about this slide in the upcoming lectures. The membrane potential is established by the contribution of several ions, mainly potassium, sodium, chloride. These ions contribute into establishing the membrane potential, okay? And so this is why the membrane potential is not exactly the same as the equilibrium potential for each of these ions, okay? As we will learn in the upcoming lecture. This is very general slide. And in neurons, okay, because as some of you mentioned, at rest, we have the resting membrane potential. So when they are not excited, neurons are excitable cells, okay, like neurons, muscles, like cardiac cells, they are excitable, okay? They do generate electrical signals, okay? And so when they are not excited, it's said to be that they are at rest. And so the resting membrane potential, when they are not excited, is closer to the equilibrium potential for potassium, okay? And this is why, because of the higher permeability of the cell at rest to potassium, okay? Now, there is another, formula which you don't need to memorize or know, the Nurnist equation. You have to learn that. This one, don't learn this equation. This is the Goldman equation. This calculates for you the membrane potential, okay? Where it takes into consideration the permeability of the membrane to the different ions, okay? And so with the Nurnist equation, it only calculates for you the equilibrium potential for a single ion. Whereas the Goldman equation, it calculates for you the membrane potential. And so it takes into consideration the permeability to the different ions. So don't learn this equation, okay? This is just for you to know. As we will see in the upcoming lectures that, when neurons are excited, they will generate action potential. This is something called action potential. And what contributes to the action potential is mainly two ions, which are the sodium and potassium, okay? So this is the end of the lecture. Any questions? Any questions? Yeah. Very good. Excellent. So she was saying with the Nurnist equation, it is 61 over the charge of the ion. So if, for example, in the exam, I give you calcium, which has 2+, right? And so you have to divide 61 by 2. And then multiply that with the log, the concentrations outside over inside. Okay, is this all clear? Okay. Any other questions? Okay, good. Let's take attendance. Okay, let's give it a go with the system. Yeah, I'll do that. No. Key. Okay, here you go, guys. Give it a go. Okay, I'll generate the key again, just for people who had a problem. Maybe try again. Otherwise, anyone had an issue, come here. Okay. There is a lot of you. Can I see what the problem is?
It's not loading. I don't know. It went off.
Connection is bad.
Ready?
Okay. Isn't all.
generate مع ضبط
Okay, let's do another generate. Okay, have a try.
I have a question. The 61 here, is it a constant value? Oh,
Some of them they say 58, but stick to the
Okay, try again. Just try again. If it doesn't work, I'll have to put you guys manually.
Yeah, it worked.
خلاص, work.
It's probably because of the internet. When I tried
Yeah,
my
the
4G,
internet sucks. Yeah, I know. Yeah.
No,
Okay,
this is constant. So if I change the values here, all you need to do 61 over the charging ion.
If you update your
calcium, you have to positive. Okay, if it's potassium,
everyone here doesn't work.
and log, all you need to do is put the concentration. So if the question I give you different concentrations in here, put the outside in here first over the inside.
so 1/10.
Yes. And then calculate this times 61.
Okay.
This is the.
1 second. Again, won't work. Give me you guys your name.
Just present all.
Hot.
Present all. Just put.
make sure it's on no.
Okay.
So the 61.
Just let me.
Everyone is present.
Okay, so please don't send email because some students, they lie.
Everyone is present.
Because I presented everyone and they still send me emails about their attendance.
I don't know.
So
We should have
they must
Walter
be
here,
not
but-
present, otherwise, you know, they've known that, you know, I presented everyone. So
It's just because of that.
all of you good students, okay?
Us, everyone is present.
No,
Okay.
Everyone is present. Focus on your learning.
Okay, teacher.
Okay.
So the 6th one you were talking about that. This is for that one, yeah? Am I right?
No. Here is the result. هذا الناتج. الحين انت انا اقول اعطيتك الحين سؤال قلت لك ان الكونسنتريشن حق الصوديوم outside is let's say 100 million
Yeah.
and inside
Log out,
is
sir.
10 just